So it's a question 68 from the tutorial book. The question says, given a matrix A, and that's a rather large matrix, here it is, components 1, 2, negative 1, 1, that's the first row, 3, 2, 0, negative 2, second row, 0, 1, negative 1, 1, it's a third row, it's a 4 by 4 matrix, and the last row is 5, 3, 0, negative 1. The question says this: given the matrix, take the columns of such matrix as vectors, and I will name these vectors like this. The first column will be my vector x1, second column will be my vector x2, x3 and x4. So I will give these specific names to my columns, like I just pointed out. First, we have to test that this is a basis for the R4. And second, we have to test if I take the third vector, fifth vector, V, with the components like so. What I need to do, I need to find the coordinates of this vector V with respect to this basis x1, x2, x3, and x4. That will be another example on the top of the example I just discussed on the previous slide, where we'll find the components of the given vector with respect to the given set of linearly independent vectors. So here it is. If I need to find this, if I want to find these coordinates of the vector V with respect to this set, I need to find the unknowns lambda 1, lambda 2, lambda 3, and lambda 4, such that I have a representation like this. And when I find these values, there will be the coordinates of my V with respect to this set. It's just another example of the same technique I just showed you on the previous slide, and another example of the same technique I used on Tuesday. But on Tuesday it was small example, so I picked another one, a little bit larger, a little bit more involved example. But in principle, the method is the same. So I need to solve for this. I need to solve for these unknowns. And it's again, when you solve for these unknowns, it's a row echelon form reduction. Again, I'm not going to do the actual details in class. I just give you, if I take this matrix to the row echelon form, and here's the set of operations. If you want to check me, if you want to verify my computations, here they are. Then the row echelon form will be like so. 1, 2, negative 1, 1. It's just a copy of the first row from here. Then there will be some different values, like this. That's my row echelon form of this matrix A. I didn't do it by hand actually. I didn't do it by hand, but I didn't do it by MATLAB as well, because MATLAB doesn't give you actually the set of operations you apply, or it does. It doesn't. I think it does. What I mean actually, of course it doesn't give you the set of operations, but if you're smart enough, if you know how to connect the set of operations with the matrices, you can extract that from the MATLAB as well. But it's maybe one day we'll discuss that. You can extract that from the MATLAB, but it's not just a direct command, give me the operations and here they are. No, it's just you have to apply some. It's a wise approach actually. You have to exercise it. Right. So first thing I see from here is that my vectors are truly linearly independent. Here's my components, here's my pivots, all 4 pivots. So my vectors x1, x2, x3, x4, they are linearly independent. Second thing I see is that because I have all pivots on the left-hand side, it means that no matter what I put here, no matter which vector I put here on the right-hand side, this V or any other V, this system will always be solvable because pivots every time on the left-hand side. So my system is indeed spanning for the R4, for the vector space R4. On one hand, it is linearly independent because we have all pivots on the left. Every column is the leading column on the left-hand side. On the other hand, because all pivots on the right-hand side, I don't have actually right-hand side written on the slide, but if you make this mental effort and imagine here the vertical bar and some random vector on the right, I said right, I mean left-hand side, some random vector on the right-hand side. Of course, when you apply your row echelon form reduction, there will be some other vector here. There will be some other vector, but it doesn't matter which vector will be there because all of the pivots still here, so it will be solvable system. So your set is also spanning. That's why this is a basis for R4. And that's how you're gonna, I mean, that's the main method, how you check that something is a basis when you talk about the space of n tuples. Gaussian elimination, again, at the core of the method. Now, if I'd like to address the second issue, how to find the exact coordinates of my v vector, I in fact have to put my v vector to the right of this matrix, and I did it symbolically like this. I just put it like this, my A matrix here, that's the whole A matrix, and that's my v vector here. Again, I fed this setting to some computer algebra system, and it gave me the actual row echelon form. In fact, the same set of operations, if I apply to this augmented matrix with a particular v on the right-hand side, if I take this to the row echelon form, with the same set of operations, on the left-hand side of my row echelon form, if I call this matrix U, on the left-hand side it will be U matrix. On the right-hand side it will be some vector, and my computer algebra system told me that the vector will be W like this. -2, -4, 16, and 12. So when I solve for these unknowns, lambda 1, lambda 2, lambda 3, lambda 4, I have to solve this system instead. That's the column for the lambda 1 unknown, lambda 2, lambda 3, and lambda 4. If I solve this system, here's the system. I'm just taking this system from this matrix. First equation in my system, here it is. It's just the first line of this row echelon form with the appropriate unknowns. Second line of my row echelon form, it's something actually which is called back substitution, which you used to call back substitution in the first semester. So I'm doing my back substitution. I'm using my row echelon form with the U matrix like so and the W vector like so. And I'm doing back substitution with my unknowns, lambdas. It's a second line, which comes from this row of my row echelon form. It's a third line from the third row in my row echelon form, and that's the last line. So in fact, actually, I have to be, if I want to be precise, what I'm going to do right now, next step is the back substitution, because now I'm going to solve. Lambda 4 solves to 4. When you sub it back into the third equation, it's a 4 here, so it's a -16 plus 4 and another negative, so it's a 12 for lambda 3. Now if you sub in these two values into my second equation, that gives you -4, take another 4 and plus 12, so -8 plus 12, it's another 4. And finally, back substitution in the last equation gives me, it's a lengthy one, let's just say -2, take 4, -6, plus 12, it's plus 6, take 8, it's a 14, and that's a 14, isn't it? Oh, how come it's -2? Where did I make a mistake? It's all right? Okay, I'll trust you. So after all of these computations, I can now formalize that coordinates of this vector with respect to this basis, and the symbol which we use for that is this symbol, vector v in brackets with a b, capital B subindex, is this coordinates. It's precisely the solution we just found. B here, it's the system, it's my basis, x1, x2, x3, and x4. Like I said, in these questions, there is a very little concepts involved. There is more computational side in these questions. If you have to do something like this in a test, like it or not, you will need to do the row echelon form with your hand. If you do your yellow book questions like somewhere at home or somewhere else, I don't mind. I strongly encourage, in fact, I'm strongly encourage you to use MATLAB or any other computer algebra system. All right, so it's nothing wrong with that. I use it all the time, and I don't see the reason why you can't use it all the time. Any questions, please?